Alright, this video is about the Doppler effect. You've experienced the Doppler effect. You don't really know that you've experienced the Doppler effect, but you have. And here's an example of the Doppler effect in action. Listen. So did you notice it was high-pitched, right? That's the Doppler effect. It's the apparent change in pitch or frequency. Apparent, so it's not really changing. It's the apparent change in pitch as an object is moving toward or away from you. So here's what causes the Doppler effect. You can actually open the Doppler effect applet that's on Haiku and you can play around with it and see what's happening. But we're going to give you a little bit of an explanation here. Okay, so in the middle here we have an object that's giving off some sort of sound wave. We don't know really what it is, but it's, it doesn't matter really what pitch it's giving off. But here we're giving off some sort of sound wave, and it is radiating outwards, and so it's going doing, 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 and traveling. Okay, so that's what would happen if everybody were standing still. But what happens is this object in the middle is going to start moving. So let's make this a little bit bigger so we can focus on this guy. So he's going to move, and he's going to move this way, and he's going to kind of catch up with the wave that he just gave off, and he's going to give off a new wave. And then he's going to move, and he's going to give off a wave, but that's going to catch up to the wave that he gave off before. And are you seeing here that he's going to move? And now we have three waves: the one he's given off now, the one he gave off before, the one he gave off before, and the one he originally gave off. So all of these waves are starting to pile up on each other, and what they will look like is this. So as our object is moving to the right, it's piling up the waves a little bit, and so you're having shorter wavelengths. If I were standing here, if I were standing right here, and these waves were passing me, I would experience the shorter wavelength, which I would hear as a higher frequency. If I were standing back here, I would experience longer wavelengths and a lower frequency. But what's important to note is that the frequency that the actual source is giving off has not changed at all. It has not changed. It just appears to have changed. So the real frequency is what the source itself is giving off, but what I perceive or what I appear to hear is a shorter wavelength sound. So as an object is moving towards me, I'm going to hear higher frequencies, and that's what we were hearing in the sound bite that you heard. It was coming towards us. And here it passes us, and now it is a lower frequency because it is going away from us. So there are calculations that go with the Doppler effect. We can actually calculate what that frequency might be. And there are many, many, many forms of this equation. I find this form to be the easiest. And it's that the frequency of the source divided by the speed of sound plus or minus, okay, we'll talk about that in a minute, the velocity of the source is equal to the frequency observed, so O means observer, S means source, over the velocity plus or minus the velocity of the observer. Okay? So get that, pause the video, get the equation down. Okay, you're back. All right, remember back at the beginning when we were graphing distance versus time graphs, and the person was going away from us, they had a positive slope. So if the source is going away, you're going to have the positive velocity. You're going to add Vs. If it's moving away, because remember if I was moving towards, that gave me a negative velocity. Remember that was the slope of that equation? So if I'm going towards, I'm going to subtract the velocity of the source. And so I find that the easiest way to remember, am I going to add or am I going to subtract? So what do we do about the observer? Because the observer also has this plus minus thing. You just do the opposite. So for the observer, your calculations are the opposite. And I'm not even going to write it down. Okay? Just remember that it's the opposite. So if our observer is going away instead of adding, we're going to subtract. If the observer is moving towards the source, then we're going to, instead of subtract, we're going to add. So the observer just does the opposite of the source. If you the source is the easier one to remember because it is related to this displacement graph that we started with at the beginning of the year. So here's a sample problem. A car horn emits a frequency of 440 hertz as it moves towards a stationary observer at 20 meters per second. What frequency sound does the observer hear? Okay, first of all, let's do a little bit of, does this answer make sense? It's moving towards us. So are we going to hear something that is higher pitched or lower pitched? Right, we're going to hear a higher pitch. So we should find that when we're done with our math, that our observed frequency should be somewhat greater than 440 hertz. Okay, if we get a number smaller than 440 hertz, we've done something wrong. All right, so let's set this up. Okay, the frequency of the source. It emits a frequency of 440 hertz. So 440 is our source frequency. We're going to just use 345 meters per second for the speed of sound. Remember that changes with temperature. It changes with the material it's traveling through. This is the speed that we used in our PAM pipes. We'll use that. It will give you the speed of sound in a problem. Okay, so the speed of sound has to be given to you because it does depend on the temperature and everything like that. So we're going to use 345. That's the speed of sound. So plain old V is just the speed of sound. All right, our observer is moving towards us. So remember from the velocity time graphs, if I'm moving towards, I have a negative velocity. So I'm going to subtract that 20 meters per second. And that's going to equal the frequency observed. We don't know that. That's what we're looking for. Divided by 345, the speed of sound. Okay, these V's are speed of sound. Plain old V is the speed of sound. Now our observer is stationary, so we can add or subtract 0. You don't have to do anything. Okay, so there we go. We set it up. Okay, go ahead and do the math. So when I do the math, actually it's a little bit easier if you simplify this first. So you have 440 over 325 is equal to the frequency observed over 345. Oh gee, how are we going to solve this? Kind of looks like a proportion. So we're going to cross multiply and divide, and we get that the frequency of the observer, the frequency observed is 467 hertz. Now before we say da-da, 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 I'm done, let us check, does that answer make sense? Remember, it's coming towards us, so that frequency has to be greater than what we were given, and we were given 440 hertz. Is this greater than 440 hertz? Yes, it is. Yay! We did a good job. Okay, so just use that as a check to see, does my answer make sense? Because if you give me 427 hertz, I'm going to double dock you because your answer doesn't make sense. All right, see you later. Good luck. Oops, there is one problem on your pretest dealing with an echo. I'm going to make a separate video, and I'm actually going to solve that problem for you to help you out with that. All right, talk to you later. Bye-bye.